When we're thinking about the ionic compounds, we have to keep in mind that we have different elements that are somehow becoming ions. And from that point, they are getting together to create new pure substances called ionic compounds. So let's see if we can have a good idea of what it means. So I'm going to go back to what we did in one of the last videos with the Bohr-Rutherford diagrams. So if you go here and you have Bohr-Rutherford diagrams, we do know that all the metals that are here on the left side, they have here same number of protons than electrons, which is amazing. However, the second thing that those metallic atom wants is to have a full valence shell. So if you think of lithium here, we have 1 electrons on the outer shell, but the outer shell actually can contain all the way to 8 electrons. So here what happens, the lithium could say, okay, I can add 7 electrons on the outer shell, or I could take away 1. And look, if the lithium takes away 1 electron, what happens here is that you have the valence shell that contains 2 and is now full. If you think of magnesium right here, magnesium has 12 protons and 12 electrons. If you put 2 electrons on the first electron shell, 8 electrons on the second electron shell, then you end up with 2 electrons on the valence shell. Magnesium here would like to have a full valence shell, like the argon would have here. However, in order to do that, magnesium has 2 options. It could find 6 electrons to complete the outer shell, or could give 2 away. And if you think of the magnesium here, if 2 electrons on the outer shell goes, you have now 8. You have a new valence shell with a complete 8 electrons. So this is what is happening here. So we have the metals here that will give, for this column here, 1 electrons. Barium, magnesium, and calcium will give 2 electrons. Bohr and aluminum will give 3. So that's something here. Now, if you look here for helium, neon, and argon, which are noble gases, here these are quite happy the way they are. They're very stable. They don't react very much with their environment. And the reason for that, here helium has 1 valence shell that can contain 2 electrons and has 2 electrons. Neon here has a valence shell with 8 electrons, and it has a full slate. Argon can contain 8 electrons on its valence shell, and here it has 8. So argon is very stable. But if you go 1 column to the left, you notice that fluorine here has 7 electrons on the outer shell, and it would love to have 1 extra one, because if fluorine and chlorine here had 1 more electrons, we would have a full valence shell. If you go for oxygen here, we have 8 protons and therefore 8 electrons. We have 2 electrons on the first electron shell, and then you have the valence shell with 6 electrons. Oxygen would love 2 electrons, and if it has 2 electrons extra, then you end up with an ion of oxygen, which will have 2 extra electrons to complete the outer shell. So let's see if I can take some notes on the board here so we can expand on what we've done and then go to the next step. So if we summarize what we just mentioned, we mentioned that atoms have 2 goals in life. The first one is the same number of protons than electrons, and that gives us this idea here of the Bohr-Rutherford diagram. Now, the second goal they want is to have a full valence shell. We noticed that from the conversation a moment ago, that the metal here on the first column, the alkali metal, have 1 electron on the outer shell, and therefore it's easy for them to let 1 go. So if they have 1 more proton than electron, this will give them a positive charge. Now, barium, magnesium, and calcium have 2 electrons on the outer shell. If that's the case, they will give 2 away to end up with a full valence shell, and therefore would have a positive 2 charge. And here we have aluminum and boron that would have 3 positive. So here, metals in the periodic table would give electrons, and therefore they would become positive ions. This one, metals, positive ion like this. So being positive ions, they have a new characteristic now. They are a particle that is not positively charged. Now, another word we can use for positive ion is cations, like this. Now, that brings us to the other side here. We talked about the noble gases. The noble gases here have the same number of protons than electrons, like we have just here behind me. We have here the fluorine and the chlorine that will want one extra electron for the valence shell, and therefore would have a negative charge. Let's see if I can move this like this. We have here the oxygen and sulfur here that need 2 electrons on their valence shell. Therefore, if you have 2 more electrons than protons, you have a negative 2 charge. And here for the nitrogen and phosphorus, we have 3 electrons extra, because here the Bohr-Rutherford diagrams shows us that there are 5 valence electrons, and in order to get 8, we need 3 more. 3 more electrons gives us a negative charge. Now, here we have the noble gases with no charges because they have the same number of protons than electrons. So here we call them non-metals. What's interesting with nonmetals is that they become negatively charged. So negative ions. And here's another word. When you have negative ions, one word that we can also use is anion. So what's interesting here is that we have these ones that are positive. We have these that are negative. And when we talk about the electricity and static electricity, we know that opposite charges attract. So in some ways, it's putting together particles that are willing to associate. Metals are willing to give electrons. Non-metals are willing to gather electrons. So if one is giving and one is gaining, it's a perfect match. So let's see if we can look at a few examples that could help us from here. Looking at vocabulary, let's see if we can add new words here. We know that metals are giving electrons, non-metals are receiving them. So when they come together, they are creating what we call ionic compounds. Now you're going to see here, if you have ionic compounds, you have the little word ion here, because it's made of positive ions called cations with negative ions or anion. So when you put ions together, you create a new pure substance, which is called an ionic compound. Now, what is the relationship or the connection between positively charged and negatively charged particles? We have what we call ionic bonding. Ionic bonding is this activity where you have an electron or more that is transferred from one atom that becomes a positive ion to another atom that now becomes a negative ion. And when you have an ionic compound, the bond that links the metals and non-metals are what we call ionic bonds. So the only way we can get an ionic compound is when you have a metal and a non-metal getting together. So let's see if we can look at how we can create some of those compounds. So here, let's put this one. So if I have here magnesium and oxygen, what's interesting? We have magnesium here that is 2 positive, oxygen that is 2 negative. That means that the magnesium gives 2 electrons, the oxygen gains 2 electrons. They have the same opposite charges, and therefore they create a compound, which is magnesium oxide. This is a great ionic compound. It is made of a metal and a non-metal, a positive ion and a negative ion, and together with ionic bonding are creating an ionic compound. Now here it's a bit different because we have magnesium that is that has a positive charge of +2 and chlorine that has a negative charge of 1. So that means here that the magnesium has 2 electrons that it can give away. But here, each of the chlorine can only, or just need 1 electron. So what will happen here is that you will need 2 chlorine atom to associate with 1 magnesium atom, because the magnesium gives 2 electrons that will go to 1 for each of the 2 chlorine. So some of you say, well, how can we figure out how it works? So here we'll do a little crisscross to figure out what is the number of each of the atoms. So if you do the crisscross, you have magnesium. Here we have a 1 negative. I'm going to put a 1. And here I have a 2 positive that will go with the chlorine, and I have a little 2 right here. If you have a 1, you don't need to write it down. There we go. And therefore you have here a magnesium chloride. Magnesium chloride is an ionic compound. Why is it? It is from a positive ion and a negative ion, and together with the chemical bonding create an ionic compound. Wonderful. A metal and a non-metal. Next one, we have here sodium and nitrogen. We're going to do a crisscross as well. We have here an A3N. What do we have here? A sodium nitride like this, because you need 3 sodium that will each give 1 electron for a total of 3 that will go to the nitrogen that needs 3 electrons. And by doing the crisscross like this, it allows us to build the ionic compound. So here, sodium nitride is a great ionic compound because it's made of a metal that is a positively charged ion with nitrogen. Here, that is now a negative ion, and together they create an ionic compound using ionic bonding. So what is keeping those 4 atoms together? It is what we call ionic bonds. So here is a great summary of what is an ionic compound and where it is coming from. If you have any clarification questions from this point on, don't hesitate to put your questions in the comments below. I'm always looking at them and answering them. And I use your questions to bring more ideas for videos on this channel. And I'm going to put here a link. Let's see if I can turn this mic. I'm going to put here a link to another video where we're going to learn more about chemistry. See you there.